So this is resulting in some really exciting and interesting, very early applications in astronomy, and I'll just talk about a few of these, but chemistry, physics, and biology. It's really pretty mind-boggling. But before I talk about that, let's just talk about what the workflow is. Because if we're going to use AI, these techniques in high-performance computing, you need to start thinking about, well, what would that workflow look like? I have my first principles numeric application today. How does that fit into an HPC plus AI workflow? And so just to start, this is a workflow for NVIDIA is if you haven't heard, there's a big self-driving car revolution going on. And it's being driven by deep neural networks that are learning to drive from watching videos and watching drivers and watching the sensors. And a lot of the leading edge research is being done on NVIDIA hardware, as you can imagine. And so we thought we'd build a car that we needed to gain experience because we're providing core technology. And so we built a car. I mean, it's just a normal car, but we put a camera just looking out the front, and we instrumented the steering wheel. That's how we started. And we just let the neural network, basically we accumulated the training set. The training set was the data, was the video, and the right answer was whatever the driver did with the steering wheel, right? And then we added, brakes and accelerator and all those things later as well. So the training starts with this data that comes in, this big training set, which is collected from video in this case. But we also use 3D simulators because, again, we need to have correctly labeled data. And one of the things we want to learn with cars is how to avoid people and cats, and how to recognize stop signs and traffic lights and pedestrians and bicyclists, and tell the difference between a paper bag and something that you could run over, and a person that you wouldn't want to run over. So 3D simulators, starting even with a lot of computer games, have been very powerful and popular way to start training neural networks like this. But then you have your training set, and so you recursively train and train and train as you train your neural network. You have to reserve part of your data set to be used. Usually they split this regression set into two components. They use part of the data they reserve just to periodically test whether your neural network is converging. But then you keep part of the data set out that you use to train at the very end to measure how well your neural network is generalizing on data it has never seen. And so that's kind of the workflow, and you kind of iterate through this. New data can come in, and you can do retraining, et cetera. And you get to a point where you've gone from 3D simulation and training through testing, and now you can do really interesting things, which I'm not going to talk about, that reduce the complexity of the neural network and the precision of the neural network in order to make it small and fast and energy efficient, and something that you can deploy in a car. And if you take that workflow then and say, what would an analogous workflow be for HPC? Well, it also can start with simulation. And the simulation can be your first principles scientific application. And you can generate, with whatever your application, your physics application, your biology application, your molecular dynamics, or your quantum chemistry code or whatever, you can generate the training set dynamically. And so you might be able to take existing codes and just use those to generate a training set over time. You can combine that training set in some domains, some science domains, with real-world data. Like you can imagine a weather forecasting model, right? So you might use something like WRF as a simulator to generate an enormous training set based on the models just by running the normal simulation and then using the simulation outputs as training input. And then over time, you can compare, you can start retraining with actual measured data of what was the weather that day in 7 days. And that can increase your accuracy. But you have the same kind of need to do regression testing and convergence testing and test the generality, et cetera. And then you get to this point where you have a trained neural network, and now you can scale out using inference-only mode. Inference-only mode is where you're not training anymore. You're just running the simulation, if you will, the neural network in forward pass only mode. And what happens when you're only running in forward pass mode, oftentimes that's faster, because it's just a single pass through. It's not something that has to, be recursive or converge. It's deterministic, and it's often much lower energy. And so it can deliver advantages in a number of different way. So here's one. You've heard about LIGO and the detection of gravity waves. The first problem that they have is LIGO is extremely sensitive. It's been called the most sensitive scientific instrument ever created. They have laser beams that they're bouncing back and forth over like a 4-kilometer track, and they have like 256 bounces, and they're able to detect a change in the length of that baseline between the mirrors that's like 1/100th of the size of a proton. So it's extremely sensitive, but this means it picks up noise like crazy, right? A car drives by 4 miles away, and you're getting a bigger signal from that than you'll get from gravity waves. So they have all these very sophisticated filtering algorithms to filter out all those different kinds of noise. And it actually took weeks to process out the noise using a cluster of conventional CPUs. They trained a machine learning algorithm, and they've been advancing that. And just recently now, NCSA has published the results of a new neural network-based model that's 5,000 times faster than the previous machine learning model. And they can now recognize and do the filtering in a fraction of a second. And this is going to enable something called multi-messenger physics, where you detect a gravity wave event, and you can actually now, if you can decode that, hey, it was a gravity wave event fast enough, people can turn their telescopes and try and see what the event was and detect it in the electromagnetic spectrum, with radio telescopes or whatever. And recently, they've done just that, which is very impressive. So the interesting thing here is, 5,000 times faster than the previous method. They're using AI to control lasers to create, basically sorting atoms by their energy level to create Bose-Einstein condensate. They're using it in the control loop of fusion reactors, leading up to ITER, which is this multinational fusion reactor project. The problem is, of course, not just containing the fusion, but controlling it so it doesn't, as it starts generating fusion, that it doesn't touch the sides of the wall, or which could not just cool it and stop the reaction, but it could actually damage things. And previous mechanisms to try to control the fusion were too slow, and they weren't accurate enough. And so they've been able to double the accuracy so far, and they think they're going to be able to, that this is the way they're going to get to the solution. And again, it's using simulation, using the first principles calculations numeric model to generate the training set to train a neural network, and then they gain an enormous advantage by having a deterministic, low latency, low energy, relatively from a computational efficiency standpoint solution. Well, this is my favorite one so far, and this is where they trained a neural network to approximate the energy of molecules, solving Schrödinger's equation. I am not a quantum chemist, but there's some really interesting things about this. They have a first principles numeric solver, DFT. I saw in the talks that there's a couple of talks later on today about quantum chemistry and using DFT at large scale on K machine to look at larger molecules and the like. The problem with DFT, of course, is that it's very computationally intense. And so I'm going to dive a little bit into this one and what they did. So they used DFT to generate a training set of some 20 million data points. And they had, they used around a dozen elements that they were generating random molecules essentially from and running those through DFT. What they were trying to achieve, NE1 is what is the name of their neural network-based approach, and it's a very simple neural network. So the researchers acknowledge that they're only just scratching the surface of the potential here. But what they're trying to do is get to a level of accuracy of DFT and other highly accurate first principles models, but at the computational cost, which is represented in time, of bad approximations that have been hand-coded so far. What they were able to do, and we need to talk about the correlation here. George Box was a British statistician. He worked in quality control, but he also did some great work in time series analysis and Bayesian inference and stuff. And he had a saying that I think is really interesting, that all models are wrong, but some are useful. And I think we all know that almost all of our numeric models for the physical properties that we see in the universe, or chemistry or biology molecules, or models, whatever, all of those are models. They're just models. And a lot of them represent approximations, and we use approximations that we know are worse approximations than the best models that we have. We often use worse approximations in the interest of having a tractable computation problem. In order to be able to run a sufficiently large simulation, we might use models that are worse than we know numerically how to solve, but those are so slow we can't use them. So here's correlation that they did. So there's a number of different molecules, and each of these red dots shows what their neural network predicted. And these are all novel molecules that the neural network was not trained on. I suggest that you take a look at the paper. It's really pretty interesting, even to someone who is not in the field like me, because they do a pretty good job of explaining it. And there's also a tutorial video online where the authors are going through and giving this in real time, and I stole some of these illustrations from them. But essentially, these are new molecules that the neural network never saw before. And the straight black line is what DFT would predict for those thousands of molecules that they were testing. And you can see that even when you zoom in, that the correlation is actually pretty good. And so the important thing is whether the model is useful. So here's kind of the definition of useful. So the upper left is, again, comparing DFT and NE1. But the green and the blue and the yellow are models that are the most common approximations that people have in use, according to the authors of the paper. So these are the faster but less accurate approximations that people have been using. And you can see that, at least from this perspective, the neural network is far more accurate. So in the couple minutes I have left, I just want to talk about what I think this all is going to imply for the future of supercomputing and AI supercomputing, which I think is going to become really a prevalent model for a lot of applications. So one thing is, let's look at the precision. we're hyper-focused on double precision arithmetic in high-performance computing. Supercomputing has always been about doubles and the like. But what you really see is if you have this kind of workflow we've been talking about, where on the far left you've got your first principles numeric simulation, that simulation requires full double precision and single precision and floating point. So you have to have a powerful supercomputer. Does it have to be exascale? Not if you're not deploying at that. The job changes in this workflow from being able to deploy an exaflop at double precision to being able to generate a sufficiently large and accurate training set so that you can train a neural network. Training neural networks require less precision than double. Usually FP32, FP16, people are even exploring more energy efficient and higher performance, but lower precision data algorithms to train. But you can see that there's a big step down there. Now that's computationally intense, and people are using thousands of GPUs to train a single neural network. That's very important. But once you have that trained neural network, as I said earlier, in inference-only mode, when you're just doing the forward passes, you don't need double precision. You don't even need single precision. Often you don't even need more than 8 bits to get the exact correct answers that you would have gotten out of FP32. And so what this means, this is your deployment model now. You need to be able to run an exaflop and very large scale at inference. That's the part of this workflow that is run at scale, and you need really large memories, lots of processors able to do a very efficient job on inferencing. And actually, ideally, you want to have one system that you can do all 3 of these things efficiently in, because you're going to be generating an enormous training set. And you don't want to have to save that out to storage. You can generate it dynamically. It's a simulation. It's an HPC application. But then you want to be able to do the training simultaneously in the same computer. Does it take an exascale system to do this? Probably not. But you need a system that can do both of those things efficiently. And then you need to be able to deploy at exascale. But it's a significantly different compute capability than saying I need an exaflops of double precision. In this model, you need an exaflops of inference equivalence. And that's considerably more efficient and smaller footprint, although you still need a large memory. It doesn't have to be as large as if the data was double precision. So, of course, I'm going to tell you that GPUs are this universal device that can do all 3 of those things efficiently, and I'll prove it to you over time. But for now, just try and take that on faith. And a number of people now, a number of systems are coming online that I would call AI supercomputers, because they can, because of the prevalence of GPUs in the deep learning world, and the combination of model and data parallel that they're using to scale training. These systems are partially by accident, but also some of them by design, being designed to do both very efficient traditional HPC and are going to be really great at running AI as well, both the training and the inferencing. So one of these, of course, is Subami 3, no big surprise. And the Pitt-State computer in Switzerland, I think currently number 3 on the top 500, powered by P100 GPUs. They set a deep learning training scaling record with that system about 6 to 9 months ago. NVIDIA, of course, because of all the things that we're doing in the deep learning world, we're building our own supercomputers out of our DGX. The ABCI supercomputer that's being installed is the first supercomputer procurement that I've seen that actually included deep learning benchmarks in the criteria, the benchmarking criteria for the procurement. And if you look at the very large Department of Energy systems that are being installed at Oak Ridge National Laboratory in Lawrence Livermore in the United States, these are going to be monsters at doing this kind of compute model. From an AI exaflop standpoint, they're already going to be multi-exaflop capable in inference mode. So they have the deployment side of that. And from a compute perspective, both for the simulations to generate the data sets and to be able to train. Honestly, at the time they were designed, deep learning wasn't at a point where it was a consideration. So it's almost accidental that they happen to be architected almost ideally to be AI supercomputers. So I think it's fair to say that AI supercomputing is here or almost here. And it's going to become, I think, a big part of our workflows. And there's even some hidden benefits from this. A lot of applications are very difficult to parallelize. Old applications, big applications, applications that have lots and lots of different science packages that can be enabled or disabled. And a lot of these applications are very expensive and difficult to parallelize and to accelerate using GPUs. And when you do, you might only get 5 times speed up or whatever. Oh, I didn't even say the punchline. On that quantum chemistry code, it's 1,000,000 times more energy efficient than DFT. 1,000,000 times. So the speed up there is just off the charts. And you're not going to get that in every case, but it illustrates that there's some remarkable potential on some of the most difficult algorithms that we try to build models that are useful for. So one thing I just want to leave you with, this could enable us to use those applications as is. Stop trying to make them run on GPUs. Stop trying to make them be accelerated. Just use them to generate the training sets. And this is how we'll configure neural networks, applications that we're going to deploy at scale. And then, of course, it's how you're going to validate results. When interesting and weird things happen, you're going to want to go back to those numeric models and make sure that it's not an anomaly. So this is going to save, I think, a lot of work just from a programming standpoint. But there's an even more astonishing statistic. So Google is a world leader in artificial intelligence today. They have Google Brain. They've been buying all the startups, the people who wrote the AlphaGo applications, all of those things. Jeff Dean leads all of Google's AI research. And they recently deployed a new translation that's many times more accurate, the Google Translate that can translate between 100 different languages more accurately, significantly more accurately than they were able to before. Their old translation code was around 500,000 lines of code. The new translator is end-to-end neural network. And because of that, it requires enormous training data, but the actual application is only 500 lines of code. So when you think about trying to maintain parts of your application that aren't even directly associated with the execution of the application, things to do load balancing and make them run efficiently, this is perhaps an additional layer of benefit that you might be able to gain. So I firmly think we're just at the very beginning of this, and it's going to change all of our lives. And I encourage you to investigate it and embrace it. Thank you.
Thank you very much.